Today's webinar topic is SimCenter 3D Response Dynamics, where we'll learn more about harmonic and random response with the newer sine and random base excitation solvers. My name is George Farah. I'm Business Development Engineer here at ATA Engineering. I'm based out of our Denver office, and I'm very happy to be joined by our own Wesley Scott for this topic. Wesley is a very experienced SimCenter 3D user and well-versed in the topic of response dynamics. Before we dive into the actual content, here's some housekeeping notes. All attendees will be muted throughout the webinar. If you have any questions, please type them into the chat, and we'll have the presenter answer them at the end of this presentation. This webinar will be recorded and will be available on our website and our YouTube channel. Before I hand this to Wesley, I want to give a quick overview of ATA Engineering, who we are, and how we might be able to support your team. ATA is a high-value engineering services company, helping our customers tackle the toughest problems. Engineering services make up about 70% of our business, and most of that work is focused on aerospace and defense. As you can see here, we have our hand in many different industries, including themed entertainment. So who are we? Well, we're a highly skilled employee-owned company with a full-time staff of around 220 people, most of them having an advanced engineering degree, as you can see on the right. We have 9 national offices across the United States, and as I've mentioned before, we have years of experience focusing on design, analysis, and test, providing high-value engineering services and great quality. This includes everything from structural design, structural dynamics, thermal, vibroacoustics, fluid dynamics, and more. Test-wise, we are the leading independent modal test group in the United States. We have a lot of experience flying our team to the test article location and to conduct ground vibration testing and using that information to help drive model design. We've talked about our engineering services side of the business, and now that leads us into the software side. We're a Siemens VAR, which stands for Value Added Reseller, who not only sells the product, but also provides software support and training to our customers. We really focus on products and solutions that we use in-house, primarily on design, analysis, and test. For example, on the design side, we have NX, we have FEMAP, Simcenter 3D, Star CCM Plus for simulation. For test, we are the first and now one of the only Siemens partners in the United States that can provide Simcenter testing hardware and software. One thing that sets ATA apart is that we sell what we use, and because of that, we've seen past customers truly appreciate our expertise with these tools. This has been proven over and over again throughout our hotline support, where you are actually speaking with a well-versed and experienced ATA engineer. In addition, we teach a variety of classes primarily dealing with simulation, and we actually generate all the Siemens training materials for NASTRAN as well. I want to encourage everyone to visit our ATA website. You can find all kinds of information on here, including our technical hotline support for customers who have purchased software from us, as well as free resources, including past webinars, FEMAP APIs, and white papers, all of which are available to download. And with that being said, I'm happy to introduce our speaker today, Wesley Scott. Wesley Scott is a project engineer with over 7 years of experience using Siemens Simcenter 3D for structural and dynamic analysis. His work focuses on building accurate finite element models to perform a variety of analyses and providing solutions to aid critical design decisions, supporting a variety of aerospace applications throughout the industry. Wesley holds both a Bachelor of Science and Master of Science in Engineering Mechanics from the University of Wisconsin-Madison. With that being said, take it away, Wesley.
All right, thank you, George, for that introduction. I will swap over to sharing my screen here. So as George mentioned, today we're going to be hosting this webinar focusing on 2 different types of solvers available within Simcenter and within response dynamics specifically. So we'll start off with a quick introduction and background of what basic analysis is for both frequency and random analysis, and then dive into both of these types of solvers. Today we'll focus mainly on the frequency and sine base excitation solvers. However, all of this is equally transferable to the random response dynamic event as well as the random base excitation event. Then at the end, we will have time to quickly recap and then open the floor to any questions you may have. So to start off with a little bit of background and introduction, response dynamics is a tool provided within Simcenter 3D, and it's a tool based on a modal dynamics solution. So this means that in order to run response dynamics, you must first start with a modal analysis, solve for the modes of the system. Response dynamics can then use that modal solution to calculate response to a number of different dynamics situations. So response dynamics can compute the response to everything from transient analysis, harmonic loads, random analysis, as well as response spectra analysis. An example of these two that we're going to look at today being the harmonic input on the left, so a series of sinusoids superimposed upon one another, as well as a random environment where the input environment is defined by a probability function rather than a explicit input function. Response dynamics can also apply these loads in a number of different types of loading conditions. So everything from a concentrated load to distributed pressures, enforced displacements, accelerations, etc. Today we'll be focused mainly on the enforced motion, since that is what this new solver type is capable of. So what are some applications that we might be interested in looking at base excitation? Base excitation is very commonly used throughout the aerospace industry to simulate a number of different launch type environments, flight environments. So it's very common for a launch provider to provide both a Sine spec and a random vibration environment that components and payloads must be able to survive for a successful mission to be achieved. These are typically provided by either a launch provider's user's guide for small sats, and also potentially from the result of a secondary coupled loads analysis specific to their payload. These environments are usually use a base excitation or enforced motion analysis to describe the dynamic environment and apply those loads to whatever payload you're interested in analyzing. In addition to the aerospace industry, a number of different industries might be interested in base excitation. An example of such would be transportation industries looking to simulate transportation loads. The example given here, you have a vehicle traveling over a rough road that can be described. The travel over said road can be described by a probability density function in terms of displacements. And then potentially there is some sort of correlation between the wheels as the front wheels go over the disturbance first, and the back two wheels are going to go over that in some amount of time delay. Components on these types of vehicles also need to survive these sorts of environments, and so base excitation is applicable to these types of problems as well. Specifically today, we're going to be looking at these two different types of solvers available within Simcenter Response Dynamics. So on the left, you'll see a screenshot of the traditional frequency and random events that have been available within Response Dynamics for a period of time now, for both frequency and random excitation types. On the right, these are slightly newer solvers available within Response Dynamics, the random base excitation, as well as the Sine base excitation. So to compare and contrast these a little, the traditional solvers are a more generic solver that can handle a much more broad class of problems. It can be applicable to enforced motion that we'll look at today, as well as other types of loads, such as distributed loads, applied forces, and multiple input problems. The base excitation solver is just that. It's specific to the base excitation type of environment, and can only apply an enforced motion at a single location. The main advantage of using this new solver over the historical solvers is that there's an improvement in the computational cost of running your analysis. And we'll see that a little bit throughout this presentation. All right, so the problem we're going to use as our example problem today is just going to be a simple generic satellite model that we'll analyze within Simcenter 2412. We're going to apply an enforced acceleration at the base legs of this satellite, and we're going to apply a flat 1G frequency spectrum from a sinusoidal spectrum from 1 to 100 hertz. The demonstration today will start from an assembled finite element model file and just create the analysis model on top of that finite element model. As I mentioned earlier, today we're going to just look at the sine and frequency events, but all of these steps are going to be analogous for the random base excitation as well. All right, so at this point, I'm going to switch over to Simcenter, and we'll do a bit of a live demo here. So starting from the .fem file, we're going to go ahead and create a new simulation within Simcenter 3D. So we'll just use the standard Nastran model and take all of the defaults in the new simulation dialog box. Within this next dialog box, we're going to give this a name. We'll just call it response dynamics frequency. And the only other thing we need to do here is define what the solution type is. So since response dynamics is a modal solver, we need to run a mode solution. So we're going to select the solution 103 response dynamics, which will enable a number of different options that are required to be present for response dynamics to solve. We can then go ahead and create that solution. This next dialog box will leave most of the defaults today. There are more nuances if you need additional parameters turned on and off. The one I will identify here is within this new base excitation event being available, there's a new dialog box radio button for selecting this purpose icon. And this just enabling this allows you to know that everything is going to be present for the base excitation event that is required for running that solution. You can solve response dynamics without having this turned on. You'll just need to make sure that all of those parameters are correctly identified. So this just goes ahead and ensures that all of those parameters are turned on correctly. We'll go ahead and click OK. Now we need to go ahead and set up all of the options for running our modal analysis. So we'll start by interrogating this collector a little bit. So a number of modeling objects have been generated by default in response for this solution 103 response dynamics. The first that we'll look at here is the eigenvalue options. So we can right-click on there and hit edit. By default, Simcenter is going to ask Nastran just to calculate 10 modes. We're going to be running this frequency analysis from 1 to 100 hertz. So we want to make sure that we're capturing all of the modes of interest. So we'll go to a frequency higher than the 100 frequency cutoff that we're going to have for the excitation. So we'll just choose 120 hertz here for convenience. We'll leave all of the other options as default. The other thing that needs to be selected in the modeling options is all of the output requests that you want to have available within response dynamics need to be selected within the solution 103 run. So once again, we'll right-click and hit edit. By default, Nastran is going to, or Simcenter is going to have Nastran calculate a number of output requests by default. We can view what it has already selected by clicking this preview button, and you'll note that displacements, SBC forces, and stresses, center stresses have all been requested by default by the solver. So we'll leave all of those options. If you wanted to, for example, add a force request for elements within your model, you would need to go in and enable that to be able to recover those responses for response dynamics. We'll leave all of those defaults to request displacements and stresses. The next thing we need to select here is telling Nastran where we want to apply our enforced motion constraints. In order to be able to apply those enforced motions in Simcenter response dynamics, we're going to need to enable those within the Solution 103 run. So we'll go up to this constraint type and add in an enforced motion location. So this will generate cards that create SBC constraints as well as add the degrees of freedom that we select to the U2 set. This will tell Nastran to generate constraint modes for each of the directions along which we want to apply forcing. So we're going to start by selecting the node where we want to apply our enforced motion, and then we're going to select all three translational degrees of freedom at that node. So that's going to create a constraint and a constraint equation, constraint mode for those 3 degrees of freedom. We don't want those 3 rotational degrees of freedom to be flexible, so we're going to go in and add in a second constraint. This constraint, you'll note, is only adding an SPC, not an SPC, and adding to the U set. And then we will just select those 3 rotational degrees of freedom. Okay, so at this point, we are ready to solve the Solution 103 run to solve for the modes of the system. We can either do that by selecting the Solve button up in the top ribbon, or by right-clicking on the Solution 103 header and going down to Solve. So we will go ahead and solve for the modes. This model is efficient enough that this shouldn't take more than a few seconds. And we are ready to go with that. So now that the modes are all solved for, we can preview the modes of our system by going down to this results collector in the navigator, in the simulation navigator, and double-clicking on our structural results. And we'll see when we expand the structural results that it has calculated 38 modes to 120 hertz. In addition to those 38 normal modes, it's also collected 3 constraint modes, 1 for each of the degrees of freedom we're going to have available to us in the response dynamics solution. So next we can start actually setting up the response dynamics solutions. So we'll need to go over to this response dynamics tab up in the top ribbon. This is frequently not turned on by default. You can visualize, you can turn this on by right-clicking on the top ribbon and selecting response dynamics to show this tab. So we'll start by creating a new modal solution, modal dynamics model, by clicking on the response dynamics tab. And we'll leave all of these as default for now. If you have a model that has rigid body modes, depending on what frequency, real frequency they show up at, you may need to modify your rigid body tolerance. But since our model is fully constrained, we have no rigid body modes, so we'll just leave all of this as default. Once you create the modal model, it will generate a couple of new collectors for you. The first we'll look at here is the modal representation. So you'll see that it's pulled in these 38 normal modes as well as the 3 constraint modes calculated in the Solution 103 response dynamics solve. We'll start by clicking on the normal modes. There is a tab on the left panel here called Response Dynamics Details View. This will give you a lot of information about the modes that Response Dynamics has pulled in from Solution 103. It'll have a listing of all of the frequencies. It'll give you modal effective mass in your 3 direct translational directions, as well as the modal mass and modal stiffness. Since we've mass normalized these modes, our modal mass should always be unit value. If you're also interested in the rotational modal effective mass, you can access that by right-clicking and turning on the rotational mass columns for this table. You'll also note that both viscous and hysteretic damping are provided in this table. We haven't set those values yet, so they're 0 for all modes. We can set those by right-clicking on the normal modes and going down to this Edit Damping Factor option. For this example model, we're going to specify 5% viscous damping in the model. And you'll see that within this table, this has now updated all of the viscous damping values to 5%. If we wanted to specify certain modes as being a different frequency value, we can simply highlight and right-click to edit damping values for specific modes one at a time. All right, so now we are ready to set up our actual loading for the model. Everything up to this point will be the exact same for the frequency event and for the sine-based excitation. So this is where the two different solvers are going to diverge. So we'll start by clicking on event and changing the event type to frequency. We're going to leave all of these as defaults, but you can specify either mode displacement or mode acceleration, even or uneven spacing. You can change how many frequency lines there are between each individual mode, as well as changing the interpolation method. So leave all of those as defaults. Then the next thing that we need to do is specify the type of loading that we're going to have for this frequency event. So we can right-click on excitations and add a new excitation. There will be 3 options for the frequency event type: translational nodal, rotational nodal, or distributed load. We're going to, for this problem, select the translational nodal excitation. This will open a new dialog box. The first dropdown is specifying what type of excitation this is going to be. So for the frequency event, you can specify either a nodal force or an enforced motion. And we can either select this graphically or from a list of available locations. And so we'll just select that location there. For the frequency event, you can also define multiple input directions simultaneously. So you'll be able to select multiple locations, whatever is available at that node based on what you selected in your solution 103, as well as applying scale factors to each direction and phase angles between each excitation. For today, we're just going to look at a single input, so we'll only select the Y direction and we'll leave unit scale factor and 0 phase angle. So now we need to define the actual input function. So we'll go into here and create a new XY function. We'll give this a name, just call this unit input Y. Then we need to define what the axes are. We'll keep the spacing as uneven. The only option here is going to be for a frequency x-axis, and you can specify in any number of different frequency units. You can specify your input as real or complex. We're just going to choose a flat 1G input, so we'll have a real input there. And then for the frequency event, you can specify your input as either a displacement, velocity, or acceleration. We'll select the acceleration, and the model units here are in inch per second, but since we just want to apply a flat 1G input, we'll change the y-axis to input in Gs. There's a number of different ways to input the XY data. You can either enter it directly, enter from a spreadsheet, digitize. So there's a number of different ways we can actually input this data. I'm just going to manually input using a text. So we're going to go from 1 Hertz frequency at 1G to 100 Hertz frequency at 1G, just a flat 1G input across that. You can also preview what you've entered to make sure that you've entered it correctly. So we'll see that the flat 1G input has been input across the 1 Hertz to 100 Hertz range. You can also visualize this in terms of different units. So you can go and right-click on the legend here, or the y-axis label here, and change this. So it's currently in Gs. If I wanted to view in inch per second, just to verify that 1G is correct, we'll get the 386 inch per second that would be expected. So we can close that preview, click OK, and then use this new input spectrum. All right, and then we'll click OK again. So now the event is ready to solve. So we'll right-click on the event and solve for the modal responses. Since we only have 38 modes in the model, it takes pretty much no time at all to solve for those modal responses. So next we can start looking at pulling some interesting data for this model. Within the frequency event type, all of the output is generated on the fly. So you've solved for just the modal solution at this point, but not actually solved for any of the output data yet. So I'll right-click on the event again, and I'm going to request a nodal response. I'm going to look for the acceleration response at the end node here, and I will request all the translational, all the translational directions. So this will open up a new plot window to view those results from our 1G input. Once again, you can change the units on the y-axis here, and we can specify in terms of G. One thing I will also note here is that, so if we look at these three translational directions, recall that we put our input in the vertical y direction at the base here. So we would expect that as you go to a static response, as you go to 0 hertz, your response along the y direction should go to 1. However, you'll note that this is along the z direction in this output direction. All of the xy output data is going to be in whatever the node's output coordinate system is. So for this node, it's actually defined for an output coordinate system where z lines up with global y. So the output that we're expecting is the z to go to 1 as you go to 0 hertz. We'll hold on to that plot for later. If we want to look at contour results, what we need to do is right-click on the event and go evaluate contour results, and we'll pick peak responses. Maybe I want to look at the stresses in my model. So we'll look at we'll grab all of the elements in the model and then select all of the directional outputs. We'll click OK. Now you'll see in the bottom here, it needs to go and actually calculate those responses. It didn't calculate that when we solved the model. So it needs to actually run here, and we'll take a few seconds to calculate that contour result. Once the contour result is created, it will create a new contour results collector, and you can double click on any of these results to view a plot of those stress results. So now we'll go ahead and return to our model. So that's an example of both the XY output as well as the contour output for a frequency event. I will also, okay, yeah, so now we'll move on to the sine base excitation. So as I said, everything with setting up the modal solve, we can recycle from the previous setup. All of that setup is exactly the same, and it would be exactly the same for a random environment as well. So now we'll set up using the newer solver, this sine base excitation. In contrast with the previous solver we were looking at, all of the output requests have to be identified before solving your modal solution, as this gets kicked out to an external solver. So we'll go ahead and edit our output requests. By default, Simcenter is going to select a contour of peak acceleration as an output type that you would be requesting. You can turn that off if you're not interested in that output. We're going to keep that output and then add some additional output as well. So I'm going to look at an XY output at that same node at the end of our satellite dish that we looked at for the previous solver. And then I will also add in the stress response. We're going to request a peak contour on all of the elements in the model. In addition to the output requests, there's also a dialog box here to specify which excitation frequencies you want to solve at. So at the default settings, this is set up exactly the same as what we had for the previous event. So it's going to solve at all of the natural frequencies of the model, as well as 10 excitation frequencies between each of those modes. With the basic excitation solver, you have a little more, you can have a little more nuance in how you specify the additional frequencies. So the intermediate frequencies can be either linearly or logarithmically incremented. You can cluster them closer to your modes versus away from the modes of the system, as well as adding in additional frequency breakpoints. We'll just leave those as all as default for this example problem. In addition, your displacements, velocities, and accelerations can either be reported as relative or absolute. This was an option in the original solver as well. We just didn't go into too much detail on that. So we'll leave this as absolute just to have a one-to-one comparison to the last solver. All right, so this will create a new base excitation collector. We once again need to specify what excitation we want to apply. So we'll right-click on the excitations. You'll note that now there's only translational nodal. There's no rotational or distributed loads that are able to be used as excitations for the Sine base excitation solver. So we'll click on translational nodal. We'll also note that in the previous solver, you were able to have a nodal force as your excitation. Now you're only able to use enforced motions with this base excitation solver. You can once again select that base input node here. You'll also notice that in this dialog box, you're only able to select one one input direction at a time for your excitation function. This base excitation solver is only able to apply unidirectional loading to the model. So to be consistent with the previous model, let's apply a acceleration along the y direction. Since I'm doing this all in the same simulation file, I have the previous input function that I had created available. So we'll use this, but I'm just going to show one thing on the new, on a kind of a dummy one here. So whereas in the previous type of solver, we were able to specify the enforced motion as displacements or velocities. Now the only option available is to specify in terms of acceleration. Since what we set up previously was acceleration, I'll just use this flat 1g input along y. All right, so now we can go ahead and solve for our responses. So again, this is going to kick out to an external solver. So it will pull up a command window when it starts solving, and then solve for all of those responses at the same time. So whereas before I had to go in and request all of those outputs, each of these contour results has already been generated and is available for viewing. When you go into looking at the results from the Sine base excitation, we'll look at the contour results first here. So you'll note that there's a number of different responses created by the output requests that we created. So by default, it generated an acceleration output. So it'll show accelerations along X, Y, and Z, but it'll also generate this magnitude plot as well. This is a function of the Simcenter post-processing tool. However, these results in the magnitude part of this collector are inaccurate. You should not use these magnitude responses. The solver itself is actually calculating the acceleration magnitude. And what you would want to look at is not the derived results, so not this magnitude calculation that Simcenter is doing, but actually the acceleration magnitude, which is output to this scalar value. If you click between the two, you'll actually notice that these are giving different values. The derived result in the acceleration nodal is done after the peak values of x, y, and z are calculated, and so it's not phase consistent. It's not frequency consistent. So the correct acceleration magnitude will be in this separate collector here. The same applies to your stresses. So you'll see that there's a von Mises elemental stress scalar, but there's also stress elemental with a von Mises option. So you'd want to use the von Mises scalar, not the values from, not any of these derived values within the elemental. The directional stresses will be correct, though. So in addition, I would also want to compare, so from our frequency response, we also calculated before the elemental stresses. So you can compare between the frequency event and this new base excitation. We'll also compare to the von Mises elemental stresses. So if we click between these two, you'll note that the results here, we get the same results between both solvers. So in addition to the contour results, we had also calculated XY functions at the acceleration at the end of this satellite dish. So to get to that, we can, from the simulation navigator, go down to spectral XY functions. This will bounce us over to the XY function navigator tab. We can go in and plot each of these responses. So we can right click, highlight what we want to plot, right click, and click plot. So this is the XY response that we get from the excitation, the base excitation solver. I'm going to go here and show the maximum value, and then I'm going to pull back from our previous analysis the other solvers results. And I need to switch these back to being in the same units. I guess we'll switch this one to being in Gs. And you'll note that you get the same peak response between both solvers in the XY plots. All right, so now I'll switch back to the slides here. So just to kind of recap what we talked about today. So there's a number of times when you aren't going to have a choice. You have to use the standard response dynamic solver. The base excitation solver is just that. It's just a solver for base excitation at a single location using enforced acceleration. So anytime you have multiple input locations or a force input or multiple input directions at the same location, or if you're defining your input by enforced displacement or enforced velocity, you have to use the event frequency or event random solvers. However, the main advantage is when you have large models with many modes. And so your modal, not only does your modal solution take significantly longer than the demonstration model that we showed today, but also each of those output requests, that data recovery starts to take a lot longer as well. And so both of those parts are made more efficient with the base excitation solver. All right, so with that, I think we have time to open it up to any questions that you all might have.
Yeah, Wesley, we got a few in the chat here that I can read to you. We'll start with this first one. For sine or random base excitation analysis, which outputs should we request in the output request section of a solution 103 response dynamic solution?
Yeah, so you're going to need to define all of the output requests you want to have available within response dynamics, you have to request that within the solution 103 run. So when you are setting up within this modeling objects collector, you'll need to have whatever data you need in response dynamics. You need to request that in the solution 103 run, with maybe one caveat to that, in that obviously I was in the presentation, I was requesting accelerations. I never requested accelerations explicitly. So I only requested the displacement output in solution 103. However, response dynamics is able to calculate both velocity and acceleration from that displacement request from that data that comes out of the solution 103 run.
Awesome. All right, another question here. Is there anything we need to know or pay attention to when using response dynamics with external superelements? Does the normal workflow apply here as well? I ask because Simcenter 3D normally works with the OP2 file as the default external superelement. However, when it comes to OP4, manual input deck intervention is required.
It's a good question. So when you are running the solution 103, you don't need to have that solve happen from within Simcenter. So you can specify within the setup for your response dynamics. So within some of these, I forget which, I think it's in here. There are locations where you can input user-defined text. So anything that Simcenter doesn't explicitly allow, like certain types of superelements, you'd be able to kind of make a workaround by putting the right pieces of information as user-defined text into the various sections of your solution 103 run. Hopefully that answered the question, but please let me know if you need more on that.
Right, got another one here. For the random base excitation event, how are the frequency recovery points determined, since the user does not get to define these like in the Sine base event?
Is this for the standard random event or for the random base excitation? Because there's two different, there's the type random as well as the random base excitation.
Random base excitation.
I believe it is consistent with the same method of definition for the random events in the standard solver. But if you send me your contact information, I'll follow up with you after. It's a good question.
All right, another one here. I guess a follow-on, but for example, in a quasi-static analysis performed for a spacecraft, which constraint is required in solution 103?
So I guess you're talking about the quasi-static solution in response dynamics, or just running a quasi-static solution 101? Sorry, I guess it's I don't know I don't see the chats, but
No, this is specifying solution 103 here.
Okay. So yeah, you would just specify so within the constraint, you wouldn't need to do the enforced motion if you're just doing quasi-static. You would just use a fixed constraint in that case.
We'll give it another minute for any additional questions here. Wesley, additional question here. When you check the box for sine base excitation, should that have included the resvec parameter?
I believe it did, but I can go here and check for you. Added the constraint. I don't think it added residual vectors, so you would need to go in and add that parameter to include residual vectors. Yeah, resvec does not get turned on by default, but by that radio button, so you would need to go in and turn on resvec. Good question.
Again, we'll give it another minute for any additional questions.
But yes, you can also see that it didn't add the residual vectors in here. So if you had calculated those residual vectors in solution 103, they would get pulled into this modal representation as well. And those would be especially important if you were running a transient analysis. Andres, I am not sure on that one. Chris, are you still around in the chat? You might have a better idea on the Simcenter SATK solver.
Chris is offline, but I can write that question down and I'll get with Chris and I can answer you directly, Andres. Give it another minute for any more additional questions. All right, that looks like it might be it for the questions. Again, this webinar has been recorded and will be posted on our website and YouTube channel. Thank you everyone for joining.